Okay, so we are going to look at two versions of the knapsack problem. So in this module, we look at what is called a fractional knapsack problem. And in the next module on dynamic programming, we'll look at what is called a 0, 1 or integer knapsack problem. Both mean the same. So what's the difference between a fractional and a 0, 1 knapsack problem? So as the name fraction itself indicates, and you already know what the problem is. So the problem is, given a knapsack of some capacity or weight, given in pounds, you have different items, say 5 items in this example, and then each item has some value and a weight. And your objective is to pick as much as possible and fill up the knapsack such that the total values of the items you have picked up is the maximum. Okay, and you can pick only one copy of each item. But the thing is, if needed, can you break an item or not? Okay, uh, that will lead to the two versions of the problem. So if you can break an item if needed in order to obtain an optimal solution, that is called the fractional knapsack problem. Now if you cannot break an item, you have to take either an item completely or its entire item or not, or just leave the item. That becomes a 0, 1 knapsack problem. So that's why it's called 0, 1. You can either pick up the entire item or just leave the item. So that is the 0, 1 knapsack problem. So we can find the optimal solution for the fractional knapsack problem using greedy strategy. And you cannot find the optimal solution, you cannot apply the same greedy strategy for the 0, 1 knapsack problem and get an optimal solution. So we have to apply the dynamic programming approach for the 0, 1 knapsack problem and come up with an optimal solution. So the fractional knapsack problem is relatively more easier to look at using greedy strategy. So that's what we'll focus on this module. So next module we'll look at the 0, 1 knapsack problem with the dynamic programming approach. Alright, so we already saw that the greedy strategy of picking just the item with the largest value may not lead to the optimal solution in all cases, right? So we want a strategy that leads to the optimal solution for all cases for the fractional knapsack problem. Alright, so just picking the value may not, the item with the largest value may not be effective. But what about picking the item with the largest value per weight? Because in the first approach I just mentioned of picking the item with the largest value, we did not look at the weight of the item. Okay, so you may end up picking some item that will occupy almost the entire bag with by just going with the largest value, and we cannot pick all the other any of the other items which may actually have more value. If we don't pick up this item 5, we may end up picking more of those other items and maximize the value of the items we picked up. So that's why it's we have to look at the value per pound. The value that an item brings per pound is what we have to look at instead of just the value of the item. So given these data, the item index, the value in dollars and the weight per pound, what we'll find is a value per weight. So it means we'll divide the value dollars by weight. So 25 divided by 3 is 8.3, 20 divided by 2 is 10, 15 divided by 1 is 15, 40 divided by 4 is 10, 50 divided by 5 is 10. So these are the dollar values per pound of an item. So now we'll pick the item that has the largest value per pound. Instead of just picking the item that has the largest value, we will prefer an item that has the largest value per pound. Okay, so that comes out to this 15 being the largest value per pound, and that corresponds to item 3. And item 3, now you look at the details, how much weight it is and so on. It is only 1 pound in total and its value is $15. So you can pick item 3 and the remaining capacity is what? 6 minus 1 pound, so you still have space for 5 pounds. So you have picked so far $15. So the next item to pick is the item with the next largest value per pound. And there are 3 items with the next largest value per pound, so that is $10 per pound. And you can pick any of those three items. You can break the tie in any order. So we'll break the tie in favor of the lower item ID, which is item 2. So item 2 has 2 pounds. So you can put the entire 2 pounds because you have space for 5 pounds. You have to also check that whether you have space for all the entire item. And in this case, yes, so far. So we have picked 3 pounds so far. So the remaining capacity is 6 minus 3 pounds. So pick the item with the next largest value per pound, so which is one of these 2 items with $10 per pound. So let us pick item 4. Now item 4 is weighing 4 pounds and you have space only for 3 pounds in the knapsack. So this is the time we can break an item as it is needed. So we can pick 3 pounds of this 4 pound item. So we'll pick 3 pounds of item 4 and its value will proportionally reduce. So 4 pounds is like $40 value, so 3 pounds will be $30. So the total value of the items we have picked up is item 3 entire item, so it's $15, item 2 entire item, so $20, plus item 4 3/4 of that item, so $30, which is adding up to $65. Now, is this always the combination you have to pick up for this given data set? Probably need not be. You could pick up, like as I said, item 5. Let us say you pick item 3 first with this strategy is $15, and then you can pick item 5. They'll together add up to 15 plus 50, 65. And you don't need to break any item here because you take just 1 pound and then take 5 pounds and you're done. So that also could be a solution, but you cannot exceed more than the 65 because that's the optimal solution, and we cannot exceed beyond that with any combination that we pick. Okay, we could prove the correctness of this, but we're not going to look at the proof of correctness for this problem. Okay, but we can take it for granted that this greedy strategy of going by the largest value per pound per weight divided by value divided by weight is guaranteed to give you the optimal solution for this fractional knapsack problem. Okay, let's do one more example quickly. So same thing, so you're given some knapsack of capacity 5 pounds here, just 4 items and the value per weight. So your first step is always to find the value divided by weight, so dollar per pound. So 12 divided by 2 is 6, 10 divided by 1 is 10, 20 divided by 3 is 6.67, 15 divided by 2 is 7.5. So now you need to find the item with the largest value per pound, which is 10, and this item 2. So item 2 now is weighing 1 pound with $10 value, and you have space for 5 pounds to begin with, so you can fill up that the entire item 2 of weight 1 pound. So the remaining space is like 5 minus 1 pound, 4 pounds capacity. So the item with the next largest value per pound is 7.5, which is item 4. You have 2 pounds of item 4. You have space for 4 pounds. So you can pick the entire item 4 in 2 pounds. So the remaining capacity is 4 minus 2 pounds. The next largest value is 6.67. You have 3 pounds of item 3. You have capacity only for 2 pounds remaining in the knapsack. So you have to break the item 3 and take only 2/3 of it. So 2/3 of 20 is going to be 13.3. That's the dollar value you pick up from item 3. The first 2 items 2 and 4 you can pick entirely. So it's $10 plus $15 plus 13.3, 38.3. So this 38.3 is the global optimum. Whatever combinations you try with these 4 items and the data and the dollar and pound values, you cannot pick anything more than anything that comes out to be more than $38.3. Okay. Any question on the greedy strategy?
No.
Okay, good. All right, so let us save this video.